Thank you for the introduction. Hi. I'm also going to talk about flexibility today, and particularly I'm going to talk about aggregating flexibility. And what I did is I benchmarked different aggregation methods that you can find in the literature based on a use case for energy system modeling and with electric vehicles. And I just want to give you a very quick motivation of why you should include electric vehicles in your larger scale energy system models. I think it's quite clear. We just have high risks due to the high peak loads and high opportunity due to the immense amount of energy storage that the electric vehicles represent. And therefore, it is really important that you include them in your energy system models, because you need to evaluate how much of that opportunity can you use and how much of that risk is really a factor in like your grid overloading, for example, stuff like that. Therefore, you should include them. But here you have a problem if you are an energy system modeler, and that is just large amounts of electric vehicles on the road already today. In Europe, for example, it's 6.7 million already. And the prediction in the stated policy scenario of the global energy outlook is that we will have 36 million electric vehicles in Europe by 2030. And if we compare that to the number of power plants in Europe, it's only 3,000 with a power of above 100 megawatts. So if you compare these two numbers, we can see that if we want to do some optimization model here, for example, a unit commitment problem, we will have a large part of our constraints only concerning the electric vehicles, while they might not have the same relevance in our model. So we need to somehow simplify it in order to run this on like a normal computer and not like giant data centers only or simulations. Now, how can we handle this problem? Like, I think the first obvious solution would be to just model each electric vehicle individually. What if my computer is just good enough? And personally, for me, the limit would be something like 100,000 electric vehicles on my laptop, where I can handle these optimization problems without needing to do too many simplification that might change like the value of my model. But if we want to look at even higher numbers of electric vehicles, and we have already seen these are really also coming, and we need to do aggregation. And as I already said, there are multiple aggregation methods in the literature, and we already seen some flexibility models in the last sessions, and often they are connected to aggregation methods. So the problem, however, here is that each time we do aggregation, we usually lose some of the inherent flexibility that the electric vehicles had in the first place, just because we model them now in a more simple manner. And at the same time, we gain runtime. And now the question is, how much runtime do we lose for how much flexibility? And each of the methods in the literature that I've had a look at, of course, they benchmark themselves. They compare to some baseline in order to evaluate how good their method is. But of course, they use some kind of benchline most of the time that they can beat. And I think there's a lot of value to having a third party who evaluates multiple different methods in just one uniform benchmarking setup in order to really evaluate how well they compete against each other. And since there is no single best approach, I developed basically such a benchmark to evaluate multiple methods. And the methods that I had a look at are these. So it's representative profile. It's a very simple approach. The virtual battery, we had a look at that in one of the presentations last day. And the flex object or flex offer and the dependency-based flex offer approach, which we also had a look at in the last section. And the benchmark is available on GitHub. You can download it, use the benchmark yourself, and you can also use the implementations that I developed for the different methods. So how is the benchmark set up? So first, we need to basically create a scenario for electric vehicles in order to have something where we can use their flexibility. And for that, we need their driving profiles and we need their price signal, basically what they want to optimize in an objective function. And then first, we calculate the true optimal smart charging. So the case where we did model each electric vehicle on their own. And then we run through the aggregation, disaggregation pipeline in order to determine how well one of the methods performs. And it's really important here to also do the disaggregation part. So you might also want to compare what you did when you just optimized and then have the aggregate load. But in multiple cases, it is not ensured that what you did when you aggregated is actually still a feasible load for the individual vehicles. So in order to evaluate really the performance of the entire method, you need to also do the disaggregation, because only then you have a surely feasible load. So and then we evaluate basically the performance by comparing the optimal to the disaggregate. And we do that just with the gap metric common in optimization, where we basically find out the relative increase in charging cost that we have with the method given as compared to the optimal case. And of course, we need a price signal for that in order to determine what charging actually costs. And I had a look at like 3 simple price signals. So a simple sine wave just for comparison, and the real market prices in Germany and some estimation of a future net load. And the results I want to show today will all reference to the real market prices in Germany. Then we need driving profiles, and I used for the MID, so the Mobility in Germany 2017 for that. It's just a data set that includes a lot of trips of real people on one day in 2017. So you can see an example here of how that data set is basically built up. We have a specific person and one trip for the person. This one is going to work at the beginning of the day, and then the same person will go back home at the end of the day. And we have like a large CSV file with a lot of these trips of individual people. And from that information, we basically chain together all the car trips, assume they are electric vehicle car trips, and then we get daily driving profiles, which I then chain together to get longer driving profiles if that is necessary. And for example, here, this is a representation of these driving profiles. So this profile would be similar to the one we just saw on the table, where a person is at home until the early morning, drives to work, is at work, and then goes back home. And depending on where charging infrastructure is then available, this will give us all the information we need in order to determine how much flexibility the electric vehicles have in order to do some smart charging. So this is the benchmark setup. And now I would like to go to the results. The results will all be about 100,000 electric vehicles. The number is chosen basically because this is the number where I can still do the optimal case, and therefore I can calculate my gap measure. And let's first have a look at the optimal result. So here we can see, for example, the loading curve that the optimal profile would do. And in the dotted line, we can see the price signal. We can see the flexibility is high enough that the vehicles basically only charge in the time frame with the lowest prices. And for comparison, we see what they would do if they are not controlled at all. So they just charge as soon as they arrive at some charging station, and then they would charge mostly in time frames with high prices. And in terms of our metric, we can see here what that means. So the gap value for uncontrolled charging would be almost 1. So it would be almost twice as expensive to do this uncontrolled charging as compared to the optimal case. And we can also see, though, that the runtime of the optimal is significantly longer than just uncontrolled charging. It's about 3 magnitudes or orders of magnitude more. And then this area would be the area where any reasonable aggregation, disaggregation pipeline would fall into, because it makes no sense to have a pipeline that takes longer than the optimal case. And at the same time, it would make no sense to have a pipeline that performs worse than the uncontrolled case, because in that at that point in time, you don't need to smart charge at all anymore. You have no value anymore. So let's look at the first method, so the representative profile, which is only arguably an aggregation method, I would say. So you basically just pick a number of random profiles, scale them up to your original fleet, and then optimize that. And then you need to importantly do the disaggregation in order to ensure that you actually get a feasible load. And if you have a look at this, we can see that it performs very well. Here in an example for 500 profiles, we only have a gap value of 0.1, so only a 10% increase in charging costs. At the same time, we saved a lot of time. And one problem with this representative profile approach is, however, that we actually get still quite a significant number of new constraints in our original optimization problem, because we still have like 500 energy units that need to be optimized. And that might be okay, of course, but if we want to go even further with even more compression, then we might want to use something like the virtual battery approach, which, as I said, we saw yesterday also. And here we just basically do our we formulate our optimization constraints for each electric vehicle individually. So, for example, the energy constraint tells us how much energy content a vehicle can have at a minimum at any given point in time and at a maximum at any given point in time. And we do that for all of our vehicles and just aggregate that together. And then we get a new formulation for a virtual
battery basically that we can also optimize. And then we importantly still need to disaggregate again though. And if we test that, we can see that it has a significantly higher gap value than the representative profile approach. And it only saves somewhat a little bit of time, but the important thing is here, a lot of the time costs are now in the aggregation and in the disaggregation step, and we save significant time in the optimization themselves. So there are methods to improve the virtual battery approach. We can firstly basically cap the maximum power of the virtual battery because it often tends to overestimate how much power it actually has in order to do smart charging. And then we get a nice increase in performance with only a very minor increase in runtime. And also, I think something that is very natural is we would first group similar electric vehicles into one virtual battery and then basically do the entire thing multiple times, multiple virtual batteries. Then we have a slight increase, we have a significant increase in runtime, but an even more value in terms of gap improvement. So both of the approaches that I alluded to until now have one problem in common though, and that is that they overestimate the flexibility of the electric vehicle. So as I said, it's important to disaggregate these approaches because we cannot ensure that the load we did and the aggregated level is actually feasible for the entire electric vehicle fleet. And it would be nice to have something that underestimates the flexibility so we can just stop after the optimization step in the method in order so we have something that is provably feasible in the optimization. We don't need to disaggregate. And this can be done with the flex offer or flex object and the dependency-based flex offer methods. And if we have a look at how they perform, so good that they were already introduced, I can skip a little bit how they work. And we can see that they perform similarly well as the improved virtual battery methods. And we can see a strong difference in runtime between the FO and the DFO approach because the DFO approach is just more complicated. However, this is not supposed to mean that the FO approach is simply better than the DFO approach because you have more modeling freedom with the DFO approach. And it's sort of a happenstance in this case that a lot of the extra flexibility of the DFO approach is not relevant for our real price signal. But if we have a look at the sine wave price signal, for example, we can see that the DFO approach performs significantly better than the FO approach. So that would be all. Here is the results in summary. We can see basically all approaches have a relevant use case. So the best performance we saw with the representative profile approach and the fastest performance with the FO approach. And we also had perfect disaggregation. But if you really want to compress the most as possible, then the virtual battery approach would be the best choice. Thank you very much. And I'm open for questions.